So welcome to Algebra 2 Honors, Big Ideas section 4.5, which is solving polynomial equations. So we're looking for zeros of polynomial functions. So far, we have in our tool belt all the tools to solve quadratic polynomials. So we have, and those have been from the last chapter. So you can solve by taking square roots. If there's no b term, you can solve by factoring. You can solve by completing the square. Or you can solve with the quadratic formula. Those were all algebraic ways to solve quadratics. And then in 4.4, we practiced factoring higher order or higher degree polynomials. So if we can factor, we know that we can use the zero product property to continue solving the polynomial function or finding its zeros. A quick example of this, something that you may have seen in 4.4, if you had x cubed minus 7x squared plus 6x equals 0. That's not a quadratic, it would be a cubic polynomial because the degree is 3. But I could factor out the GCF, the greatest common factor of x, and I would have x squared minus 7x plus 6 left. And then I could factor that into x minus 6 times x minus 1. And bring down the greatest common factor. So now I have three factors, and if I use the zero product property, I get x equals 0, x minus 6 equals 0, which means x would equal 6, or x minus 1 equals 0, which means x would equal 1. So I can find these three zeros for that function simply by factoring. In today's lesson, we're going to add a couple more tools to our belt in case the polynomial does not factor. So the first tool that we're going to add is called the rational root theorem. It looks way more complicated than it actually is. The rational root theorem says if you have a polynomial, that's why we're going to call it p of x, and we don't know what degree it is, so we're going to say it's the nth degree polynomial. And we're going to let the coefficient be called a sub n. So a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus, and we don't know how many terms it has, so we've got some dot dot dots, plus a sub 1, x to the first power, plus a sub 0. So this looks a little bit intimidating because the coefficients, we don't know how many there are, so we can't label them A, B, C, D, E, so we just label them with the A with the subscripts. But it's just a regular polynomial in standard form. The rational root theorem then says any rational root of the polynomial is of the form P over Q, where P is a factor of A sub 0 and Q is a factor of A sub n. So if we break that down, and then we can do an example. If we take our constant term as well as our leading coefficient, if there is a rational root, it's got to be a factor of the constant term over the a factor of the leading coefficient. There is not guaranteed to be any rational roots. It could be irrational or even imaginary, and then we wouldn't be able to use this theorem, but this theorem is helpful for any root that is rational. For example, if we just had this quadratic and we were looking for the possible rational roots, because let's say we didn't have the tools to solve the quadratic, if we just wanted to list out the possible rational roots, I would take the constant term and the leading coefficient. So I'd say x equals plus or minus all the factors of 10, which would be 1 and 10, 2 and 5, over the factors of 3, which would be 1 and 3, and then I'm going to take every possible combination of that numerator and denominator. So the possible rational roots here would be x equals 1 divided by 1, 2 divided by 1, 5 divided by 1, 10 divided by 1, and then 1 divided by 3, 2 divided by 3, 5 divided by 3, and 10 divided by 3. and then plus and minus of all of those, so now I also have the negatives of those. So -1, -2, -5, -10, -1/3, -2/3, -5/3, and -10/3. So we're going to write them all out. It's still a lot of choices. This is 16 choices, but compared to infinite choices that I would have if I didn't have this theorem, 16 compared to infinity is not very many. With this particular example, we could actually solve this one by factoring it to show that the roots that we get are actually on our list, so we could go ahead and do that. This actually factors into 3x plus 5 and x plus 2. And so if we solve that, we would get x equals -5/3 and -2. And you can see that -2 and -5/3, they're both on our list, which means that the rational root theorem is doing its job. So here's how we're going to use the rational root theorem. When we are trying to find the roots of a polynomial, we would always try to factor first. However, if we cannot factor it first, then we can use the rational root theorem. So number one, we're going to list all of the possible roots by the rational root theorem. Number two, if you have a graphing calculator at hand able to use, then you can graph and find a good candidate for a root so that you're not stuck doing guess and check forever. Of course, if you don't have a calculator, then you would just start doing guess and check. Just pick one. So we would use synthetic division, or if we need to, possibly this would be long division, to factor out the root. So that means actually we would be taking out the factor that gives us the root. So the vocabulary there is a little bit informal. And then we can repeat those steps until we have the polynomial broken down into linear factors, or until we have it broken down into a quadratic that we could use the quadratic formula if it doesn't factor. So once we get to a quadratic, we know that we are home free from there. Let's do an example. So let's look at finding the zeros of f of x equals 2x cubed minus 3x squared minus 8x minus 3. It has 4 terms, so I would try to factor this by graphing or by grouping it, but it's not going to group. We can see that because 2 to -3 is not the same ratio as -8 to -3. So because I can't just factor it off the top of my head, we're going to go ahead and use the rational root theorem. So we're going to list the possible rational roots. That would be the factors of 3 over the factors of 2. And although this term is actually -3, because we have plus minus of these numbers, it doesn't actually matter whether you take that as 3 or -3. I would have plus or minus 1 and 3, and then 1 and 2 on the bottom, the factors of 2. If I write out these combinations, then that would be x equals 1, 3, 1/2, 3/2, -1, -3, -1/2, -3/2. 8 choices, which is not terrible. So let's just start trying. I'm going to set up synthetic division. So 2, -3, -8, -3. And I'm just going to try x equals 1. So I'm going to put 1 on the outside and see what happens. If this is a root, then I know that I will have a remainder of 0 because it means that the factor of x minus 1 must divide cleanly, since this would go through the point 1, 0. So I'm going to drop down the first term, and then I'm going to multiply and add, multiply and add, multiply and add, and I did not get 0, which means that x equals 1 is not a root. And as much of a waste of time as that feels, at least it allows us to cross off that choice. And this actually tells us, if we're graphing the polynomial, it does tell us that this polynomial would go through the points 1, -12. So that's kind of a consolation prize if we happen to be graphing it for later. But now let's just try again, try another one. So let's try x equals 3. 2, -3, -8, -3. Drop down, do your series of multiplying and adding. And in this case, ding, 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 we get 0 for our remainder, which means that x equals 3 is a root or a 0 or an x-intercept of this function. And so what I would have left, now that I've taken a cubic and divided a linear factor out of it, I would have a quadratic left, which is 2x squared plus 3x plus 1. So I need to keep going with this. I can either factor it or use the quadratic formula or continue from my list, from my original list, trying to divide out other factors. But in this case, I can see that this is going to factor into 2x times x, 1 times 1, and a plus sign and a plus sign, which means that my original polynomial, f of x, must be my quadratic that I had left over times the factor that I divided out, which was a factor of x minus 3. And so that means that the zeros of this function, by the zero product property, the zeros would be at x equals 3, x equals -1/2, and x equals -1. And I'm getting those from setting all of those factors equal to 0 by the zero product property. I can also check to make sure that the -1/2 and the -1 are on my list. If they weren't, it means that I did something wrong. Since they're rational, they should definitely show up on the list of possible rational answers. But they do, so we give ourselves a pat on the back, and we feel very satisfied about that. The second theorem in this lesson is called the Irrational Conjugates Theorem. The Irrational Conjugates Theorem states that any irrational zero that a polynomial has comes with its conjugate pair. So the word conjugate kind of means its partner or its pair. Examples of conjugates would be root 5 and -√5, or 1 plus the square root of 2 and 1 minus the square root of 2. So they're not opposites of each other. The irrational part becomes the opposite symbol, but the rational part stays the same. What this theorem says is that because the polynomial itself has nice, neat coefficients that are rational, if there is an irrational zero, it would have to come with its conjugate, so that if I multiplied everything out to put it in standard form, I would end up with a nice, neat set of coefficients here. An example of this is the directions that would say build a polynomial with zeros of x equals root 5 and x equals 3. The hidden instruction in here that you would have to first realize is that if there is a zero of x equals positive root 5, that means then there is also a zero of x equals negative root 5 by this theorem, the Irrational Conjugates Theorem. So I'm going to build that polynomial from the zeros backwards into the factors. So y must equal, if the zero is x equals 3, then the factor would be x minus 3, which is just going backwards from what we had been doing earlier in the chapter. If the zero is x equals root 5, then the corresponding factor would be x minus the square root of 5. And if x equals negative root 5, then the factor would be x minus negative root 5, which is x plus root 5. This is a polynomial with zeros that are given to me, so I technically have satisfied this question, although this is not in standard form, which is generally asked for. And right now all I have is the linear factorization. This is called the linear factorization because these are all linear factors, as in x to the first power for all of these. There are several different levels of simplification of your answer, or factored versus expanded, and they each have a name, so it's important to know what the name is so that you don't do extra work. I can go ahead and start multiplying this together. If I multiply x minus root 5 and x plus root 5, those are differences of squares in a way, that x times x would be x squared, and the inner term of x times negative root 5 and the outer term of x times positive root 5, those cancel out. And then the last term, that would be negative root 5 times positive root 5, that's negative 5. So I get x squared minus 5 when I multiply those two factors together. This would be called either factored with rational coefficients, or you may see this in the textbook as, it might say, write as a product of linear and irreducible quadratic factors. So irreducible means that if I gave that to you as a factor problem, you wouldn't actually choose to factor it into x minus root 5 and x plus root 5. So that's considered an irreducible quadratic factor. If I continue to expand this and I FOIL these, then I would get x cubed minus 3x squared minus 5x plus 15, and then that would be called standard form for the polynomial. So if it doesn't say to put it in standard form, don't go through that extra work of putting this polynomial in standard form. But that's how we can use the irrational conjugates theorem to help us build a polynomial. One more example of building a polynomial that I'd like to do with you is if we wanted to build a polynomial that has zeros of x equals 0, x equals 3/2, and x equals 1 plus the square root of 3. I also would like this to have a leading coefficient of, let's say, 6. I want to build a polynomial here. So if I start doing what I did last time, I can take the zeros and turn them into their corresponding factors and then start multiplying them out. If you want to go ahead and try this on your own, feel free to pause the video and try this on your own. By the irrational conjugates theorem, I can look at these zeros and I can say, well, this one's rational, so that's fine. This one's rational, so that's fine. But 1 plus root 3 is irrational, which means it must come with its conjugate, which would be 1 minus root 3. So I'm going to go ahead and add that to my list. Then I can see 4 linear factors, so that means this is going to be a 4th degree polynomial, and I can start writing it out. I'm going to wait until I get to the end, and then I'll put a y equals on that. So the factor that would present me with x equals 0 would be the factor of x minus 0, which we know is just x, so you could write it as x as well. The factor that would give me the 0 of x equals 3/2, you can maybe do this in your head, but it's going to use a little bit of work, that if x equals 3/2, then 2x would equal 3 if I multiply both sides by 2. So 2x minus 3 would equal 0, which presents us with the factor of 2x minus 3. Because I'm not allowed to write x equals 3/2 because we don't want any fractions in this factorization. So that one's done. The next linear factor would be x minus quantity 1 plus root 3. And the next one would be x minus quantity 1 minus root 3. So if all I had to do was build this polynomial, that's a pretty good start. I still haven't thought about the leading coefficient yet. which I'm going to need to, and I should probably put a y equals on that, but this is a pretty good start. If I thought about what the leading term would be if I multiplied all this out, that would be x times 2x times x, which would be 2x to the 4th power. If I want the leading coefficient to be 6, that means let's just change the steepness of this, the vertical stretch of that, and if I give this a vertical stretch of 3, then the leading coefficient will be what I want it to be. So now let's go ahead and put this in standard form just for the practice. It's a little bit trickier when you've got a binomial root or a two-term root, should I say. And so because of that, we can do this one of two ways. We can either do this as a FOIL in a FOIL, which is, it works, but it's a little bit tricky. Or we can rearrange it, which is a little bit of a magic trick to kind of help this out. So I'm going to rearrange this by distributing the negative. This would be x minus 1 minus root 3. And then over here I'd have x minus 1 plus root 3. And I can regroup these. I can group the x minus 1s together. Putting those purple parentheses there does not actually change those expressions from what I have them. And now if I look at this, this looks like a difference of squares. I would have x minus 1 times x minus 1. So x minus 1 quantity squared by taking those and having them grouped together as x minus 1 is all one entity. And then my inner term would be x minus 1 times negative root 3, and my outer term would be x minus 1 times positive root 3. Those would cancel out. Then the last term would simply be minus root 3 squared, which is 3. So if I continue to expand this out, this would be x minus 1 times x minus 1 minus 3. That would produce x squared minus 2x plus 1 minus 3, which is minus 2. So these two linear factors actually just bring us that nice quadratic. I still have a factor of 2x minus 3, and I have a factor of x, and I have a 3 that I'm going to need for that leading coefficient of 6. And then I would continue from there. So let's go ahead and expand the binomial times the trinomial. That would give me 2x cubed. And then I would have minus 4x squared and minus 3x squared. So that's minus 7x squared. And then minus 4x and plus 6x. So plus 2x. And then plus 6. Times 3x gives me 6x to the 4th power minus 21x to the 3rd power plus 6x squared plus 18x. And I'll go ahead and put a y on this. And if you check this with your graphing calculator, you should see that the zeros would be at x equals 0, x equals 3/2, and then you would have to check the decimal equivalent for 1 plus root 3, which would be about 2.732, and 1 minus root 3, which would be about negative 0.732. And so that would be a good way that you could check your work to make sure that you had done this correctly and all of our requirements are satisfied. That's pretty much it for the first part of 4.5, which is just solving for the zeros of polynomials. I'm going to give you a video here in just a second on how we can actually use that to get a pretty decent graph of a polynomial, along with a couple other tools in our belt. So stay tuned for that one if you need more on polynomial graphing.